I'm Anna Basiri. I'm talking about open geospatial data science at Alan Turing Institute with a showcase of one project that we do with collaboration with Alan Turing Institute. And so perhaps I can explain how we have benefited from the Turing Way, and you can contribute as we have done, and we enjoyed it very much. As Martin said, I was supposed to be supported by two fantastic colleagues of myself, but unfortunately Terry couldn't be with us, so I'm trying my best to be as great as Terry is, but please forgive me, you know, it's just a bit of late notice, so I try to present as best as I can, but you know, it can't be perfect. So what we can expect today is I will introduce a little about Turing Way, then I will talk about the project that we run, and it's all about missing data, and I will talk about, you know, how we can actually use missingness as data. Then perhaps Hyesop at that point can take care of the open geospatial element and open platform, and so we can discuss how we can collaborate together. You can see that I put the famous picture of, you know, the airplane that was supposed to have some armor during World War, and we mapped the point of bullet points, and we thought the point that got bullets are more vulnerable to the enemy, and so we should put the armor there. But there was a genius mathematician, Abraham Wald, that said, no, actually the point that doesn't have any bullets is more vulnerable because the airplane fall off immediately and they don't manage to come back home. This is usually the picture that you see whenever there is a talk about survival bias or missing data. But I recently got the presentation from Katie Bond when she talked about the black hole, and I thought this is really perfect. The reason for this is because we are going to talk about missing data, and the way that they map black hole is actually looking at the changes that the black hole actually have on the surrounding wave. But more importantly, whenever Katie gives talk, she talks about the element of open science and the community that collaborated. So if you have attended or even saw some of the picture of the EPFL Open Science Day, she mentioned about 22,000 community that contributed to the open research, because the whole way that they mapped black holes a few years ago, more than 200 researchers, was like, well, of course, you can't image something that is like black hole and absorb everything. You should look at the changes that it made to the surrounding place, and they had a lot of simulation. But in order to capture any observation about the changes, the only possible way is to have a very, very big telescope, because that black hole is 1.3 millimeter. And from that far distance from the Earth, you need to have a telescope of the size of the whole planet. So the only possible way for this was crowdsourcing the whole work. And by crowdsourcing, we mean, obviously, you need to have a telescope in different parts of the world, but also in terms of training model, you need to crowdsource the model, debias based on the contribution of a lot of scientists, but also lay audiences and participants. And if you look at the libraries and packages that she has mentioned in her talk, some of them are not, you know, that fancy. They're NumPy and, you know, the thing that we all use. And so I'm going to give you a kind of low budget version of the talk that Katie gave on behalf of the community of 200 people. I thought that that's fantastic. I can talk about the science of how we can actually use missing data as data, but also then talk about the community and collaboration element. So as I mentioned, this project is basically funded by UKRI Future Leader Fellowship, but also quite a few other funding. We've got very generous partner, including Alan Turing Institute, Ordnance Survey, Uber, and Google. I'm talking about the major role of Alan Turing Institute, our National Data Science Institute. I'm going to talk about how you can participate and contribute to Turing Way, which is one of the projects that is actually giving guide to have reproducible, ethical, inclusive data science. So well, Turing Way is basically have got the mission to make reproducibility as easy that it would be even difficult not to do it. So the moonshot goal is too easy not to do. It is a community-driven project, so there are a lot of people working on this from different skill sets and backgrounds and expertise, try to give the guidance about the reproducibility and best practices and how to make it inclusive, to make it beneficial. And with any background and level of knowledge, you can contribute. There are some very techie programmers who are doing fantastic job there, but also there are completely non-technical people who are writing down the best practices in book chapters, or even translate the book chapters into other languages, so it is accessible for to many other people. Some people just proofread the chapter. So you can contribute, and it doesn't necessarily need to be based in a university which is a partner university. No, it is open to anyone. If you attend any of the presentation or any of the co-working cafe, you would see that there are some people on the other side of the planet. So I would strongly advise you look at the GitHub, the Slack channel, the website, and you get to know there are a lot of tutorials how you can actually contribute to the open science, because of course there are some good practices, but for geospatial data science we are still a relatively limited number of people working, and we want to grow a lot. I think Hyesop will talk about some of the things that he has used in our project, and they were given by the community of Turing Way. So I would like to just leave Turing Way at this point and tell you a little more about the project that we have, and try to give you an example of the project. So the project that we work at the University of Glasgow, and it is partnered with Turing Institute, is about missing data as data. So if you just want to remember one thing about us, it would be missing data and bias in data as useful data. In a statistic, missingness can have like three main ways, although there is a really nice book by Professor Hand, David Hand from Imperial, that is called Dark Data, with the same terminology of dark matter, that has got 15 types of missingness. The thing that you don't know, you know, you don't know, you don't know, you know, you don't, and I don't want to bore you with that. But there are three main data that can be missed. The first one is the missingness that is completely at random. For example, I may forget answering one of the questions on a survey. It happens to all of us, and it's not a big deal. It's completely at random. You can just make an average and replace the value that you don't have. Sometimes, for example, here the age is missing, so you can just make an average and assume that is okay and use the data, or simply remove that record. Sometimes missingness is at random, but it is related to some of the other variables. For example, you see that the missingness of age happens a lot for women, because there is a society pressuring to remain always young and so on, for example. So in order to calculate the value for that missingness, you may just consider the variable and model that into your model. So for example, you may average just women to calculate the value of the age, or you may go a little fancier and find the correlation and so on. The one that we are the most interested is that mysterious missingness that is not at random. That is the kind of missingness that you intentionally don't give us to. For example, if I ask you how many pints of beer you had last night, if it is a double digit, you may not say that. You prefer not to say it. If I ask you your income, you may not say it because it is too high or too low. So missingness is a function of its own value. And so this is the type of missingness that we are the most interested, because we know that there is a reason for not giving the data. And if we could find that reason, we can design a better system, we can design an inclusive system, we can just design our survey to make it a bit better in terms of make it a bit better. For example, instead of asking you how many pints you had last night, I can say on average, or over the last couple of months or so. So this missingness that is not at random is very interesting, but for human beings, that's a very difficult to get because human beings are, you know, predictably unpredictable. You know, one day you may answer one question, the other day you don't. So it is very hard, although we are working on that, and there are some initial results that we've found, and I would love to talk about the elements of missingness not at random for human being. But the easier way is look at innocent sensors, because sensors do not give your data if they can't. So for example, if there is a thermostat that doesn't work beyond 70 degrees of centigrade, and if you see in your data that there are some point that doesn't match with your data, you don't have any data, you can assume it was above 70 degrees. So we thought the easier way to deal with that relationship between missingness and the value itself is to look at sensors. So the good example of this is creating 3D map from blockage of GPS. We know where the satellite is, we know where we are. If you don't receive the signal, that means there is an obstacle between you and satellite. As the satellite moves and it becomes in your view, you can estimate the height of the building. And if you've got so many other people, you can estimate the shape of the building. Sometimes signal goes through windows and get to us, so it becomes weak and attenuated. So that level of weakness tells you a little about the type of material it has gone through. Sometimes it bounces off from the facade of the building, and some of the characteristics of the signal changes, like polarization or the strength. So you can estimate what is the facade of the building. So that's fantastic, because based on all the errors that we hate all the time, you can infer a lot about the surrounding environment of your mobile phone. This is not just for GPS. This is also true for other signals. For example, we tried with Bluetooth and Wi-Fi. You can count the number of people because our body absorbs signals. So based on the attenuation and weakness of signal, you can count how many people are in the room. This is fantastic because, you know, for energy consumption modeling for a smart home, that's great. You know, you can turn on lighting if there is a person in the room. You can even estimate where are the walls and windows if you have that. There are a wide range of applications from energy consumption modeling, but or autonomous car, more accurate positioning and navigation, like drone navigation. You know, in future when you receive your pizza from a drone delivery coming through to your window, you know, you will see that, you know, 3D maps are quite important because, you know, we can't compromise the level of certainty around getting pizza or not. There are some studies showing that, you know, as you go on top of a tower, you're more likely to not survive from a stroke or heart attack just because emergency services do not have the 3D map of the building. So just 3D maps are quite important and very useful for many, many applications. And if we could create them based on a methodology that is free practically, not like laser scanners and surveyors, you can get it anywhere else, then that would be fantastic. So we implemented the whole methodology as I mentioned. So basically we need some data, we try to model and see how much of the data we can actually extract about the surrounding based on the impact on the signal. So we collected a lot of data and we went through the procedure. But the only thing that I wanted to say, I started with the term GPS and I continued with GNSS. GNSS is just the general term for GPS. So GPS is the American system that is a global positioning system, but we've got some other similar system like Russian GLONASS, like European Galileo, we've got Chinese Beidou, we've got Japanese QZSS, we've got Indian, Korean systems, and we will have our UK global navigation satellite system at some point. Whatever is the name, I don't know, some people say Newton. Brexat is my favorite term, so because we don't have access. But regardless of what the system, we are using all the signals that are with same sort of constellation. Anyway, how we do that, thanks to Google, since 2016, the latest version of Android from 7 onward, we can have raw GNSS data. And by raw GNSS data, I mean the kind of received signal S-train signal to noise ratio and some of the characteristics of the signal. So on our phone, we can capture those data. And if you go around your building and just capture those data from the location APIs and measurement APIs that is provided to us, then you can go through the procedure that I just mentioned. So basically, we get the 2D map. We use the 2D from our generous partner, Ordnance Survey, but you can work with OpenStreetMap, which is again globally available. The reason that we work with Ordnance Survey was because they also have 3D maps, so we can actually at the end evaluate our results and see how we are doing in terms of the accuracy. So we get the 2D map, we capture some data, and we try to, we can create the 3D point because there is a cutoff point. So there is a rate between satellite and the receiver. So we can assume that the received signal strength is higher if the satellite is in view, and it is lower if it is not in view, or completely zero if it is blocked completely. So when we create the cutoff point, the intersection between the building and the ray, then you can have a classified signal based on line of sight and non-line of sight. And you can just retrain and see where is the optimum height that cuts most of the points. So you can estimate the height of the building. So it is really simple procedure. So you get 2D map, which is, again, I would say globally available, and you create some point data, you get location, and as well as received signal strength and some other feature. You classify them based on the signal characteristics and estimate the height. So it's based on a simple bootstrapping algorithm, and you co-train signal classifier. The best part is you don't need to have an initial input in terms of what should be the non-line of sight signal, because you can co-train them together. So we went to several places. We started with a residential place. We continued with a UCL campus because we started this project when we were at UCL. It was perfect location because there was only main quad of the building and the rest was open. So the only building that can block the signal was the UCL main quad. But also we went to Urban Canyon, the area that there are so many buildings that block each other. And we collected a lot of data. In rainy day, Terry made me to go and collect data, and I'm going to complain for the rest of his life about this. So we collected a lot of data, and our results really fantastic because we estimated, for example, if you've been at UCL, the main quad, we estimated something between 55 and 59, and the actual height of the building is 55. So 55 to 59, and the actual height of the building is 58. So we were quite accurate. We tested in different locations, in residential, in Urban Canyon, and all the time we get, based on 4-parameter bootstrapper logistic regression model, we get something around a meter accuracy, which is comparable with our national mapping agency. That is fantastic because we can actually give some feedback to them if there is a building that demolished and they need to update their map, so they can actually go, or we can have a global 3D map of the whole planet, because in some area like West Africa that we barely have a 2D map, we just need some volunteer to go and collect some data, and based on our algorithm that is now available as a Python package, you can actually download and work with that. And there is a GNSS mapper that actually map 2D map and your observation into 3D map. This is fantastic because all we need is just some volunteer to collect some data and use a freely available, globally available GNSS signal and our Python package. So we have proved the concept. So we know that is working. We know that it works in different area, but we need to scale it up. So if I just want to summarize until now, I should just say that, well, we work with missing data. We want to make sure that in the time of big data, where we say data is everywhere, if you have some island that doesn't have any data, that means something. We should make some inference about them. And we should be able to create some statistical model can actually work with missingness, because the whole statistic is basically working with data. And if you don't have data, there are a lot of problems around many of the assumptions that we have made. So we are trying to use that. But as I said, we just started with the proof of concept. We need to scale it up. So I'm showing a kind of a prototype that my colleague Nathaniel actually did that. And perhaps at some point we will talk a bit better. We need to make sure that we get more data, not just because our package and software works with a lot of data, but first of all, look at the nature of our data. Most of it is already line of sight data. We see the satellite. So there is no value in that in terms of mapping. Nothing is blocking it. Sometimes the blockage happened way before the actual building by another building or so. So again, that's not very useful because that's again redundant data about another building. But more importantly, we want to make sure that we can create 3D map for the rest of the planet as well, because there are a wide range of applications like emergency services and energy consumption modeling and so on that actually need 3D maps. And not every country have got our, national mapping agency like Ordnance Survey that actually provided that. So we should scale this up. But there is a problem with missing data. You cannot distinguish with the case that you don't have data or you don't have a volunteer to give you the data. So that's how we should make sure that it is as inclusive as possible. So the way that we design the app is supposed to be as inclusive as possible, because for people who live around the campus of the university, you can assume that they're a bit younger, so virtual reality can attract them to use the app. For people who are a bit older and certain time of the day they go out, maybe bigger fonts should be embedded. So the design of the app needs to be very, very embedded in the system. So diversity by design, if that's a good term. And at the same time, we need to have a very good understanding of what is the optimum number of observation that we want to have. Because going back beyond this project specifically, at the time of crowdsourced data and big data, we always deal with bias. For example, there are 2 billion of people on Twitter talking about Brexit. And we know that they are not representative of the whole society, because when the actual referendum happened, it was 50-50. I haven't seen a Brexiteer on Twitter in my followers and following, but they are there and they voted for Brexit. So how can I understand what is the effective sample size of a big data, of a crowdsourced data? There are some nice work by Professor Meng of Harvard, and we work a lot with each other. And I should here acknowledge the work that we do with Professor Chris Bronson and funded by ESRC. We are trying to make sure that we have a good understanding between the quantity and the quality of big data, and we can understand what is the effective sample size of a 2 billion people in a randomized survey. So we try to find the relationship both spatially and socially, and try to understand the whole society a little better. For example, if you say there are crowdsourced data with the size of, 14,000 or 140,000 people contributing, if we know that, what is the population? If we know that, what is the correlation, similarity between people or the data, we can just understand it's not as big as we thought. And these are some of the work that we are at the moment doing, thanks to that project. And I just wanted to say, it's not just missingness, it's also bias. And we have a special interest group at Alan Turing Institute, again, about participation in data science. We want to understand where we need more data, because the size of data is a bit deceiving us. Sometimes we believe that this is really good and fantastic, but we need to have a better realistic understanding of the quality of the data, the distribution of the data, and the component like spatial and spatial and social element of that. So I will try to stop here and just say, if you have any idea about the missingness, if you want to collaborate with us on the project, use the data, 3D map or social aspect. If you have got some data that has got some suspicious missingness, I would love to hear from you, because we have some statistical model that works with missing data. They're quite nice and complicated, but we need to test it in different scenario, different practices, and see if they are as amazing as we think. And so we want to hear from you. So please contact myself if you want to have any collaboration. And I just wanted to say I'm extremely grateful for UKRI and all the partners that we have. And of course, funding bodies like Royal Society and ERC and ESRC and many others that actually pays our bill to be able to work on this project. And I leave the whole K-link element and the bias to Hyesop. So Hyesop, I will stop here. If you want, you can share your screen and continue.
Sure, okay. 1 second. Can everybody see my screen? Yeah, okay, great. So hi, my name is Hyesop. I'll continue the talk. I think Anna explained mostly about the geospatial aspect of open science. I'll continue to talk about openness and crowdsourcing and reproducibility. So the title I put here is How Do We Crowdsource Geographic Information Using a Turing Way Approach? I think we know mostly about what crowdsourcing is, and Anna just talked wonderfully about how representative one project can be while the others are biased. So we know what the pros and cons of crowdsourcing is. Our ultimate goal is to develop a crowdsourcing app, as Anna introduced, but given that we had lockdown in the beginning of the year, and we still have some kind of travel restrictions, we decided to currently focus on the literature part and to see whether we can find some underrepresented sources. So the focus of my talk would be mostly on threefold: to introduce our project that we just initiated, and I'll introduce some key components of Turing Way and how Turing Way can be applied to this sort of VGI review. So, okay, first things first. So what are we up to? So, as some of you may know, there is a term called VGI, but assuming that most of the audience don't know, I'll just talk about what VGI is. VGI is defined as geospatial contents provided voluntarily by individuals. And this term was introduced by Michael Goodchild in 2007. And in this article, I think he describes crowdsourcing as a method of obtaining needed ideas, services, or content by contributions from a large group of people. And this is a simplified procedure, which is divided into 4 different parts. And mostly people are looking at the final product, which is the product after the validation. And many papers focus on the quality of the data. But today, we focus more on the participants, because we believe that participants' contribution can give diverse outcomes. So, as I've just talked about VGI, so there are some projects which have a really nice representation of crowd, while most of the studies which I have looked at had bias participation. And participation bias, or participation inequality, means that a small percentage of participants contributes a very significant proportion of information to the total outcome. And it's also known as long-tail effect, or 90-9-1. So this means 1% of people create content, 9% edit the content, and the rest of the 90% view the content without contribution. So what does it lead to? So So most of the data which we all see in Google or OpenStreetMap is fine itself, but some of the data for underrepresented groups, for example, nursery or childcare, has not been put on the OpenStreetMap until recently, because I think some scholars have claimed that you're not giving the access to tag a nice, beautiful icon for childcare, which is really important for moms and dads. But this, because the gatekeepers didn't allow it until recently, they had problems. But now I think people now can start tagging. So these kind of hidden data are all over the place. So if we leave that, then we'll have less social support to those kind of people. But our question is, this is one sample, but do we see any other biases from underrepresented groups? And do these biases actually lead to a different outcome? So we're quite interested. So does gender difference really matter to making an OpenStreetMap? Does age matter? Do old people create different maps? Does language barrier really matter? So we can think about these, these indicators and this question. So this research actually questions similarly, but in a different way, as does the active contribution from underrepresented group in BGI create diverse outcomes? So we are currently looking at different indicators from the body of the literature. We are reviewing systematically and transparently. So this is our kind of motto for that. I think for systematic review, formulating a question is very, very important, because I think you have to follow a certain type of framework. And here we introduced a spider framework to help list our search terms in the database. So according to the spider framework, we use our question to categorize the keywords into this kind of form. So if you want to search in Web of Science, Google Scholar, you can put underrepresented groups and put a spacebar and put diverse outcomes. You can type in different combinations to get the most optimized outcome. And you can see different results when you put different search terms. So currently our review journey is as shown here. So from 1 to 5 is mostly done. We got our research question, we got our research, the review protocol, we've documented it, and we identified the concepts and so on. But I think there are still some tasks that we haven't really done. And we are showing this journey because just the two of us reviewing this will take a really long time, and it won't be as persuasive if we don't open it to the public. If we don't show it to in a really in a reproducible way, you won't see as nice, as transparent as possible. So we think that there is a need for reproducible research even in the review, and we need collaboration to boost our speed to write our document in an open Turing way, and we need doing that, we need effective communication. So we are using a Turing Way approach. So I'll just briefly talk about some of the components of Turing Way. And you see that these days, many people just upload their codes and say, oh yeah, you can install the packages. But sometimes my code doesn't work. And if you use a different language, and if your computer is based on that language, French, German, CJK, or other languages, for example, sometimes it will have problems in reading the data. Even if you have UTF-8, it will have a problem. That's what I experienced recently. So there is a problem. I think in order to do a reproducible research, I think you need to design your research really well. I think that's the first key important thing. But the second and third is communication and collaboration. So you have to be really open to receive different comments or feedbacks through your online repo or communication channels. And for collaboration, you really need to set a nice ground to do teamwork. And for doing that, you have to understand which person does which role. And this is an example of personas and pathways. So, for example, you can expect a team with a group of 4, and there might be experts in reproducible research and show expertise in your own theoretical knowledge, but without any coding experience. You might have a new PhD student. So you have to, I think, set a nice score for those who really have less experience, or for those who have experience and driving it forward. So that's a kind of brief explanation of Turing Way and how collaboration, well, the key components that should be considered for collaboration. So we show here a really brief example of our review. So before we call for collaboration or communication, I think as you've seen from our journey, we formulated our questions. We do all the basic research design. And here, I just wanted to show you some of our early results, because I think writing just a bunch of text might not really interest people. So we think that, okay, even though we did a systematic review, we can show you interesting results. So do you want to join? So that might be quite persuasive. So here we used a package called Bibliometrics. It's an R package, and it deals with BibTeX. And to do that, we can just use R in our own machine. But I think for non-coders, I think the open container is really important. One of the containers I want to introduce is called CodeOcean, and this is an online container, and it can read in any programming language. And if you have an academic account, you can get 10 hours, and if you ask for more, they will give you more hours per month. So this is the basic interface of our of the CodeOcean platform. And you can see on the top right here that from just a click of reproducible run, you can get all the images listed on the bottom right. So you can see that, oh yeah, if you have the code, here's the result. So these CodeOcean maintainers are quite serious about verifying. So if you want it to be as transparent as possible, you can submit your code, and they'll come back to you after 3 days and say, we will accept it or we'll decline it. If we accept it, that means the code is successful and everything's fine. If you are declined, then there is a problem. So recently, for this talk, I have tested and submitted my codes and results, and they said, okay, yeah, it's wonderful. Yeah, so that's how it went. So the details is, I'll just go over a few slides and say, okay, we used 2 databases, and you're familiar with the BibTeX file here, right? So we type VGI, and this is the database that you would get as a basic outcome. But here, the next process is to make it in a machine readable form. So that's how it went on that code on the previous slide. And you can see here, by typing Volunteering Geographic Information, you can get the top 20 authors by total citations. And you can see that VGI is a growing field, in terms of the number of articles Sadly, I don't know why it's trickling down a bit, but I think there is this kind of action happening from just exploratory research. So you can talk to people like that. We have done this. So this is the top 20 articles that have been cited, and you can see here that these are the journals. And the journals by itself, it's here, and you can see that the International Journal of Geoinformation has been published the most about VGI, and it's followed by transaction GIS, remote sensing, and so on. And you can see the corresponding author's country as like this, and you can see US and China is leading this field just by the number of documents, I would say. But you can see that single country publications is colored in blue, and pink means multiple country publications. So that means international collaboration is happening already in this field. And by showing this map, you can see that these are the number of documents colored in different colors, but also you can see that the collaboration is happening everywhere, especially in the US and Europe, China and Australia, and so on. So this is a kind of just a naive search, but you can see from the early data extraction. So what we're really interested in is, does the study actually consider representativeness? But some studies say yes, some say no. So you can show people that this is the actual gender bias happening in such studies, and there are also having age bias as well, because it's crowdsourcing, and the people who are contributing have a certain type of age. So after we go through all this review, we want to place different indicators into this 4 different layers. So we see that age and sex will go to personal profile, time of investment will go to individual lifestyle factors, and cultural issues will go beyond the national boundary. And we'll actually develop this figure in a meaningful way. So this is what we're doing at the moment. So finally, I would end this in my talk, let's say, with this slide here. So if you think you want to contribute in this ongoing project, please reach out to us. If you're an expertise and want to learn a little bit more about VGI, please join. If you want to do data analytics, please join. So this is quite open. We're working in a transparent way. So we are also willing to consider your persona as well. So just want to quickly finish my slide here, and then leave Anna to talk.
Yeah, I just wanted to just summarize. Yes, we work with missing data, we work with bias in data, and we want to work with you. So reach out to us if you've got some good data set with some missingness that you think there is suspicious sort of reason, or you want to contribute to Hyesop literature review and be one of the co-authors of our papers and review his work or just redo what he has done. We just want to work with you. Thank you.
Thank you both. It was really exciting set of presentations. I see that we had a bit of discussion already started in the chat, but I would like to move the discussion to the video if we can. And let's start from the bottom, where Anita Grazer asked whether it would make sense to try to transfer the statistical model you mentioned to animal tracking data.
Okay, one of the things that I didn't mention is, first of all, let me say this is really great question that I think I need to explain a bit better. That's why. You know, that missingness that I mentioned is the function of the value, requires a lot of domain expertise. You know, you should have a good assumption to examine. So the hypothesis that you say, okay, might be because the income is high, or, you know, that happens, or the bullet got to engine, so the airplane fall off. So you need to have a good domain expert. I'm not the expert in animal movement, but I can give you an example of human movement and how that would translate into that. For example, we know that you know, people may not give the trajectories of their movement if they are moving around their own home, because that's home address, and there is a sensitivity around the privacy concerns and so on. And the statistical model that we have developed, example of how it works, you know, in usual statistics, there are some ways to even calculate basic statistics like average and the standard deviation. When you do have missing data, you're not even allowed to do a statistical simple measure like a standard deviation. Let me give you one example. If you have a set of okay, let me share. I try to be as brief as possible, but let me just share and give you just one example here. You know, I don't know, do you see my whiteboard?
Yes.
Okay, perfect. So for example, if I've got 0, 0, 0 and 100, these are 99 zeros. The average of the above data set is all of the data that you've got, which is 1. I've got 0 plus 100 over 100. If I follow the standard deviation, which is basically says xi minus x bar over n, this standard deviation becomes something like 1 plus 1 plus 99 over 100. And it is like 99. So it becomes something around 9 point something. This is not a good variation, because all the changes that you have, because, you know, if you look at the data, most of your data is 0. The only data that actually drag the whole thing is that 100. So this is basically a fat tail or thick tail that we have. So if I ask you, if this is like weather, every day is sunny and one day you had hurricane, if I ask you about the variation of weather, if I ask you what is the weather usually, you would say it is always sunny, mostly sunny. You wouldn't say it is 10% hurricane time. This is because it is not normal. This is not Gaussian distribution. So your standard deviation should be the absolute of x minus x bar over n. So it becomes 1 plus 1 plus 99 over 100. Absolute of that, which is something around 1.9. So you see, these are in a statistic very the same, but if you have missing data because you don't know about the distribution of data, you're not allowed to use this. You're just supposed to use this. So the problem with missing data is that the simple statistic that need to be visited all the time. And for that reason, you need to look into the underlying reason and expert view and check everything in place. So for human, for example, mobility or a trajectory, that's a really good example. Yes, of course, we can actually make some assumption about the missingness. For animal, I actually don't know. That is why I call for collaboration, because we cannot do this on our own. We need to have some expertise in the team. So Anita, if you have, well, not if, I know that you have worked a lot with animal trajectories, so I would love to work with you with those data sets.
That's an amazing answer. Another question from Jeremy Morley in chat. If you impute missing data and add it into your data set, what is that large data set now useful for? Since you've included your hypothesis in the data distribution in the possible test data, does it actually improve the situation?
Oh, that's a really good question, Jeremy. Let me just say hello. Jeremy has been a really good supportive of our project. there are two things that we do with missing data. One is the imputation. We tend to impute the data based on another data set. So if you find a relationship between missingness and the missing value, we tend to, what we call it, mass imputation. In that case, it is useful for usual statistics, like inferring about the average income or so, because it is imputed based on another data set. If I just impute it based on the actual data set, like average it or something like that, then there's always a level of uncertainty that you need to at least get it. But the part that is quite useful, if we don't impute, we just calculate the relationship between the missingness and the missing value. You can actually use that as a golden rule for any other data set that you have some missingness. So it is kind of a scalable. So yeah, it is not useful for the very same data set, but if you combine several data sets and have mass imputation, you should be able to just have some hypothesis and try to reject or accept the hypothesis. Did I answer your question, Jeremy?
Yes.
Yeah, great. Francisco asks, it's more a comment. Francisco, do you want to jump in and comment by yourself, so I don't have to quote you?
Hi, how are you? Sorry, I didn't hear the whole presentation. I came a bit late. But just thinking, I guess that there are a number of approaches that I could think of that could be potentially helpful in that situation. So depending on what is the final purpose of the modeling, but potentially one of the approaches could be to think about two different distributions for the missing data and for the actual data where you are capturing the process. So then you could model the two set of data using different distributions. So that could be a potential approach. But yeah, so I mean, happy to talk about different statistical approaches later on.
Yes, okay. That's a really good approach, and that is the kind of approach for mass imputation that I mentioned to Jeremy, because there are two mechanisms of recording, and you can actually assume that the kind of uncertainty is almost the same. However, in real world, usually that doesn't happen. We don't ask the same group of people in two surveys the same questions. What we can actually assume, this is the brilliant part of the geospatial element, because your location can act as the foreign key to all the other data set. For example, if I look at the neighborhood that I live and ask about the income from some people that are randomized for that survey, and look at another survey that asks again about the income from the same neighborhood, I also have got the census data as a calibration. And then what you suggested is possible. But for many other cases, this is not the way. Because if you don't have the location, you don't have a kind of linkage between the two data sets, because you don't talk to the same group of people, or at least you don't know if they are randomized in the same way. The only linkage between the two data sets, or more than two data sets, for mass imputation is the location. So I agree, your approach is very good if you've got different recording mechanism, but that is subject to have the location. So I'm very lucky that I've worked with all location data, but just remember, for card transaction data and so on, there is no element of location. So it is really hard to find the two data sets that you actually use the recording mechanism. But absolutely correct, yeah.
Great. I don't see any unanswered questions in the chat, because some of them were answered during the talk. But I have one which is less scientific. What was the motivation to actually start studying missing data? It was some kind of frustration that you didn't have what you needed to?
Yeah, I think the mother of any innovation. Well, of course, yeah, I think that's, well, we all deal with some errors in data. But to be honest, the whole motivation started when we realized that there are some errors in data, not necessarily missing data, that happen to data because of a reason. For example, we worked with OpenStreetMap and we wanted to find the navigation, but we realized that there are some wrongly tagged features just because the contributor were lazy to put it, this is corridor, they put a tunnel. So the car navigation went through that. So we thought, okay, we need to have some rule to extract them to make the quality of the map better. And we realized it's not just error. So if you look at other aspects of quality, which is not just positional accuracy or thematic or semantic accuracy, it is also incompleteness of data. You would realize that there is a huge potential. And also I think one of the good part is some of the papers that we read, again, I should give a bit of credit to Professor Meng of Harvard, who actually gave a fantastic talk about representativeness and how missingness happens in a statistic. And there isn't that much of solution for that. We just try to impute. And we thought, okay, we have access to the golden spatial data that they don't in usual statistics. So there is a solution in our hand. Yeah.
Great. I don't see any more questions. And since it's 2 minutes past 4, I think we are free to close this session for today. I want to thank a lot to both of our speakers. It was really, really good, including the Q&A. And we will have another brown bag session, most likely on 25th of May, but it's not confirmed yet as far as I know. So follow us on Twitter and we will let you know soon. That's all from us for today, and have a nice rest of the day and nice weekend.